next row operation, and so on, and after a certain number of row operations, we'll say E. Okay? What we got was a bunch of matrix multiplications that are the same as doing those row operations. And what this gave us, well, that's a matrix that we can multiply by A to get I. We saw from one of our conditions, if one of these exists, if it works on the left-hand side, then it will also work on the right-hand side. And it will be the inverse, right? So you get the EK times EK minus 1 times EK minus 2, blah, 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 all the way down to E2 times E1. This is A inverse, right? And we did this in a simplified form whenever we took a matrix, 1, 2, 3, 4, and then we super augmented it with the identity matrix. So we made this super augmented matrix where we did a bunch of columns at the same time. We did row operations to get that this was 1, 0, 0, 1. Whatever row operations we did to this, we did the same ones here. That's the same as multiplying these one after the other. And whatever this is, A inverse, whatever that is. Yes?
If we wanted to be precise there, would we say it's EK, E2, E1 times I equals the inverse?
Well, multiplying by I doesn't change anything.
Yeah, I know, but like just for being really precise, I guess, is that the same thing?
It is the same thing. Why would that be?
Because like then we define it as doing all these to the identity matrix gives you the A inverse, right? All these row operations. So just like being precise for that. Would that be?
That the definitions would be the same. There's one condition in which we might get a little confused, and that is, what if there aren't any? So in order to get the row reduce A to I, or to do the row operations until we get to I, we didn't have to do anything. Well, that would have meant we started out with I, right? So we get I, and then there was nothing there. There was nothing that we needed to multiply by. So if we started off by saying there's an I here, and then an E1, and dot, 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 down to EK, there's no E1 down to EK, then it's no longer empty, and we can say that the inverse of I is I, and we would sort of, it would look nice. Now the alternative is to just say this is empty, and empty multiplication is just I. If there's nothing to multiply together, then we're just starting off with multiplying 1. It's the same kind of convention, if you remember back from calculus, your teacher might have tried to sweep this under the rug, but we have this convention that 0 factorial. There's nothing to multiply together, right? And so we said this was 1. The convention is there's an empty multiplication, so what do we call it? We call it 1. If we adopt that convention, then we don't have to put an I here to say, what did we initially do to A? Well, we initially did nothing to it. We did no row operations, and then we did a bunch of row operations. That's what, if I put an I here, and I read this off and I said, what this really means is, these are the row operations I had to do on A to row reduce it in this order. What did I do first? I didn't do anything. Next step, I did this row reduction and this row reduction. I can leave off that first step of not doing anything. So they would be equivalent. Oh, actually, the point that I'm trying to get to is that this is a factorization of A. Just like we might write 6 equals 2 times 3, we're writing this matrix as a multiplication of a bunch of other matrices. This is a special kind of factorization, and this is also a special kind of factorization. A factorization that we can do, we can kind of think of these like these were prime numbers. These are not really prime matrices, but they're kind of simple. They're simple matrices. They're elementary matrices. So this is a special kind of factorization. Another kind of factorization that we could do is if we take any matrix, we can write it as A times I. Well, that's kind of a trivial factorization. It's valid, it's true, but it's kind of, yeah, you know, you didn't really tell me anything useful. Whereas this gives us a lot of very useful information about A, right? It tells us exactly how to row reduce it. You just do these row operations. But it's still, this is still a valid matrix factorization. So this is the idea that we can sort of factor matrices the same way that we can factor numbers, because we have a multiplication. Well, that's great. How does this differ from this? In this case, we're looking at invertible matrices only, and in the whole numbers, in the integers, there's only two invertible elements, 1 and -1. And so we can factor 1 as -1 times -1, or -1 times -1 times -1 times -1, blah, blah, blah. We get a similar thing in this situation. We could come up with other factorizations. In the integers, we only have two invertible elements. In the matrices, we have lots of invertible elements. Okay. What was I going to talk about next? So we were talking about all different ways that these were equivalent to each other, all different kinds of ways that we could say the same thing. A is invertible matrix. Ways that look, this and this look very different from each other. For 2x2 matrices, we had another special way of determining if it was invertible or not. Something that we could almost figure out just by looking at it. For example, this one. Well, we could say, we call it this one. In the case of two matrices, we could just look and see if one, or two vectors, we can see that one is not a multiple of the other. But there's a special number that we can compute for this matrix that tells us if it's invertible or not. You want to remember what that is? So we're going to go on to that. Another statement, let's call it statement Z. Determinant of A is non-zero. If A is we knew how to compute the determinant of A if it was a 2x2 matrix. Just a quick review, we multiply these two numbers together, and then we subtract from that what we get when we multiply these two numbers together. So the determinant of 1, 2, 3, 4 is -2. Not 0. Okay. What we're going to do now, I guess I'm not going to actually prove this. How should I say this? Well, let's try to get close to a proof. So what we did before when we computed the determinant was we row reduced this thing, right? We row reduced this thing until we got some kind of form that we would get it to be the identity matrix. So what did we get? Oh, now I remember. That was a lot of work. What we got was, in the end of it, 1 over the matrix is A, B, C, D. 1 over A D minus B, C times the matrix D, A minus B minus C, right? Okay. So this is the inverse. And so what we saw is that the inverse only exists if this thing is not 0. And we call that the determinant. This is just one way of coming up with this number. Doing this kind of row reduction and then figuring out, is there something that has to be non-zero in order for this to work? And if there is, we call that thing the determinant. We did the same thing for a 3 by 3 matrix. We get some kind of expression in terms of all of the elements of the matrix, but a lot more complicated. I doubt anybody tried that whenever I gave that as a challenge. The same thing exists for other matrices as well. And it turns out that the exact same condition works. So if we describe the determinant as that number, the number that has to be non-zero in order for it to have an inverse, and if it is non-zero, then it does have an inverse. Then this is sort of true by definition for any size matrix. Now, without going through the work of showing you how we actually arrive at this, I'm going to show you how to compute it by some examples. For the 3 by 3 matrix, you've actually seen this before, but let's do it anyway. Okay, so a 3 by 3 matrix. A, B, C, D, E, F, G, H. The reason I'm sure that you've seen this before is because you took Calc 3 and you saw how to compute the cross product, which they defined as the determinant of a special matrix. If you didn't know what a matrix was, or didn't know what the determinant of a matrix was at the time, you could have looked at one of the other ways of computing the cross product. So, how do we compute the determinant of a 3 by 3 matrix? We pick a row or a column. Okay? Oh, first of all, we have this rule. Let's say we went across the top row. In Calc 3, they often told us this was the way to do it. So we pick the top row and we go across. We take A times, and we use the vertical bars to indicate this is the determinant. For this element, you block out things in the same row and column, and you get a submatrix. So the determinant will be A times the determinant of the submatrix minus, so as we went from here to here, we went from plus to minus B. What is the submatrix when we block out this column and this row? D, F, G, I. And then we went from minus to plus C times, block out this row and column, we get D, E, G, H. I'm writing vertical bars to indicate the determinant, which is why I was a little bit thrown off when the rest of it. Okay. And then when it's a 2 by 2, we know how to compute the determinant. Multiply these two together, subtract from that the product of these two things. So let's do one by hand. For similar reasons to why we have an invertible matrix has to be square, we only define the determinant for square matrices. It kind of doesn't make sense otherwise. It's also the case that there are no non-square invertible matrices, because you have to be able to multiply on both sides, which means that the inverse would have different dimensions whether you're multiplying on the left or the right, because they would have to match on the left and match on the right. There's an extension of the idea of the inverse to non-square matrices. I think it's called like the pseudo inverse or something like that. Actually, it does turn out to be mathematically useful. But I already only have 6 people in class. If I start talking about the pseudo inverse, it might go down. I don't want to look at the book. I don't need it. I want an example. That's what I want. Oh, no, back to the definition. We actually need, there's more that we need to talk about. We chose to go across this row. We could have chosen any other row, or in fact, any column. All we have to do is keep in mind the rule about the signs. Plus, minus, plus. Whether it's plus or minus depends on where the entry is in the matrix. It alternates. Plus, minus, plus. It alternates just like this. Minus, plus, minus, minus. As you move over to the right or left, or you move over up and down by one spot, it swaps. If you think really hard about the row reduction operations, you'll see that whenever you do the row reduction operation, if you end up subtracting something from this row, and then you want to use that row to cancel out this, the negative that you apply here becomes a positive being applied here. And it alternates as you go down, right? That's sort of like, can give you a feeling for where this plus minus comes from. If I just write it like this, and I don't tell you where this is coming from, we're out of time. I told you how to compute the determinant. Go home and do it yourself. Yeah, so the significance of this is that, well, we could use any row or column. We usually pick the most convenient one. And so if I did something like, let's do this in 1, 2, 3, 0, 4, 5, 0, 0, 6. I got some really obvious choices for what I'm going to use as my row or column. The one with a lot of zeros in it. Because I'm only going to need to take this one and compute it on this submatrix here. And now, I just take this row or column. Well, I know that it's going to be this one, this one, this one, this. But that's the same as saying 4 times the submatrix that you get when you get this minus 0 times the submatrix that you get. You block that out, which is fine. The same kind of rule applies, even though we use a special rule for convective. And what you get is that the determinant of this thing just turns out to be 1 times 4 times 6. Right? You pick this one, and then you get this submatrix. What do you get for the determinant? You pick this 4, and then you get this submatrix, and now you're down to just one number. So a special rule applies when we have, this is called for obvious reasons, a triangular matrix. I don't think we've said that in class, but they say it in the book quite often. We've never had a reason to say it in class yet. Yeah, when you have a triangular matrix, the determinant is just the product of the diagonal. a really simple condition on if it's invertible or not. Let's do it. 1, 2, 0, 1, 0, 2, 3, 6, 0, 0, 5, 4, 1, 1, 1. Triangle, where is it? 0, 0, 0, 1. Immediately I look at this thing and I know it's invertible. How? Well, this column is not a multiple of this column, so I know these are linearly independent. I know there's no linear combination of this one that's making me this one because these are all zeros here, this has to be a 5. And these linear combinations here, well, that'll never give me a 1 here because these are all zeros. Saying this very quickly because I'm already out of time. Also, just the same, it's equivalent, just like all these things were equivalent. What's the product of this? Well, if I want to know it's invertible, I don't even care what the product is, just that it's not 0. And the only way it could have been 0 is if any of these things were 0. So if nothing on the diagonal was 0, then there's a triangular matrix. All right. You're also very nice to stay, even though you don't have to. Appreciate it. And for the people at home watching the video all the way to the very end, trust me, you should have been in class. I've seen your exam.